Hi, everybody. Welcome to class today. So yesterday I had you, as a fun exercise, go on to the virtual spirograph webpage. And some people maybe have this toy at home. And if you mess around with it, use different colors, put the pen in different slots on the the circle, the inner circle, you made some really good looking designs. Those shapes are called hypotrochoids, and that's something we're going to look at, I think, tomorrow. But to build up to that, we're going to look at today something called an epicycloid. An epicycloid is what happens when you have a circle, like here. Usually, I think of this circle being bigger than the smaller circle, but actually, the circle that's being rolled around around the other one can be the same size or bigger than the inner circle, but we're generally going to have the outer circle smaller than the inner circle. And what shape would a point on the rolling circle, in this case, you can see this point right here, what curve would that trace out as the small circle rolls around the big circle? Now, you'd have to be told whether it's rolling whether the center of the circle is rolling of the smaller circle is rolling clockwise or counterclockwise. So I'm just going to tell you that this circle, the smaller one, is going around this way. You could take a minute on your paper to draw. What do you think that will look like? And what would it look like after eventually this circle, this little one, is going to make it back to its original point? What if it went around twice? What if I rolled it around 2 times? What would that look like? So take a minute. I see a couple of questions and comments. I see. So just okay. One speculation is that it will be a circle itself, and then I hear some things about flower petals. So take a minute to mess around with that. You can do some chat on that. Okay, that's good. So a lot of people are saying they're expecting some kind of flower-like thing, and that would make sense. Remember the other day we saw that a circle just rolling on a flat ground, a point on that creates something that looks a little bit like a semicircle or like half of an ellipse. And if I roll the circle a second time, it would make another one and another one. So if I'm rolling around a circle, well, I might expect to see these things, but they're kind of like stretched out and they're curved around the circle. And that's why some people are saying it's like a flower. Now, the question is, how many petals should this flower have? And will it sort of trace over itself if I do a second time around? Let's take a look. Here I have, not this one, but rolling epi. So here's the situation that that we were looking at, and I'm going to actually trace it out. And you can see here, so it makes this 5-petaled flower. But if I bring it back to the beginning, and if I move this guy up, this one up, this lets me go around more than once. So now take a look. And the second time around, it traces right over the first time around. So I do get this flower. But we're going to see that if we change the size of the circle, maybe the rolling circle is 3 instead of 2, take a look at what happens. It makes these bigger things. But not only that, when it gets to the end, it's not overlapping anymore. And when I do it again, rotate it a little bit, it ends up looking like that. And those do resemble the things that you made when you did the spirograph thing. Spirograph is a little different because the circle is rolling inside the bigger circle, and we'll look at that one tomorrow. But our goal today is to find the equation of this thing. And we do that through a series of 4 questions. And this is the 4th one will lead us to the general formula. So today is carefully organized. Okay, so here's our first scenario. This is not the epicycloid question. In this scenario, what's going on? I wonder if I can I make that bigger? Well, it looks like I can rotate it. I can distort it. I don't want it to be distorted though. Okay. Okay, so it's a little bigger, it's a little distorted, but it's okay. Okay, now this is not the epicycloid. We're building up to that. What's going on here is I have a big circle with radius 10, and I have a small circle with radius 2. But in this one, the small circle is not rolling around the edge of the large circle. Instead, kind of like a planet going around, you know, like if the sun's in the center here and the Earth is going around the sun, the center of the circle, the small circle, stays on the circumference of the big circle. So I call this one, I'll use the word floats for this. When you see me say floats, I'm talking about where we don't have to worry about the physics of how fast it would actually spin while it floats. Because if it's rolling, we don't have as much control. But if it's floating, this smaller circle is floating around the center of the big circle, the center of the small circle staying on the circumference of the big circle. And there's more information you need to know then. So you need to know the radius of the big circle, which I'll call B. We need to know the radius of the small circle, which I'll call A. We also need 3 more pieces of information. We need to know, is this circle, the center of the circle itself, is it going clockwise or counterclockwise? So I'm gonna call that, so the circle is floating clockwise. Okay, because it's told to you, sorry, floating counterclockwise. So that's the 3rd piece of information I need. The 4th piece of information I need is while this circle is floating, it's also spinning, kind of like the Earth, the way the Earth rotates as it revolves around the sun. I'll call that rotating. And it's told to you in this case that it's rotating counterclockwise also. So the point on the circle is also going counterclockwise. But you could have any of the four combinations. You could have the circle floating counterclockwise while the circle itself rotates clockwise, or any of the four combinations. But there's a fifth thing I need. I need to know the speed, not the speed that it's going around the circle, but the speed that it's rotating. Well, it's how fast is it rotating in relation to how fast it's revolving. We need all five of those things. And I'm going to bring up the sketch, which is called floating epi. And you have links to these sketches. And here I can put in B, you can see B here and A. And the D1 and D2, those are whether the point's going clockwise or counterclockwise. If it's positive one, it's clockwise. If it's negative one, it's counterclockwise. The D2 is the revolution, and the D1 is the rotation. So right now, this is the scenario. One more thing, the speed. And in this case, in this question, it's given to us that the speed rotating is 10 times, it's rotating 10 times faster than it is revolving. So when this circle, for instance, makes it over here, it's revolved 40 degrees around. The point on the circle will have revolved 400 degrees. So it will have, the point on it will have revolved more than a full thing. So those are the five pieces of information that needs to be given to you. If you take a look over here, I put 10 for R. So for every 1 degree it rotates, R is 10, sorry. And now if I come over here and move the C value, we could watch. Hold on a second, why is that? Okay, you can watch it go. So it looks a bit like the thing we made, but it's got this sort of loop-de-loops in it. Okay, a couple of things to notice here. How many like pedals does this thing have? You type it in, and what do you notice about that? Any prediction or speculation about how we might be able to predict how many pedals there are? Well, it's a good prediction to be 10, but it turns out that it is 9 pedals. So it seems like it's one less pedal than the number. And that is what is generally going to happen. So I'll bring this back. Just look at it again. Let me try to go to a specific point here. So here I like to go to the 30-degree point, close to it. So you see when, oh, let me move back to the other thing because I have a better picture of this. So that doesn't look like 30 degrees. That's okay. This looks like it's only about 12 degrees. Now the t value is going to be, t is going to go from 0 to 360. And the t is going to be measuring this angle here. The angle that the center of the floating circle is sort of making with the horizontal line there. So if this is 12 degrees, this angle here would be 120 degrees. Notice how that 120 degrees is with relation to this horizontal point, because this circle is sort of floating around. And while it's floating, this like little satellite, this moon, it's like the Earth is going around the sun and the moon is going around the Earth. This like moon has actually moved 10 times as much, so it's 120 degrees. Now to find the equation, I like to think of it two ways. First, I think, what if this circle doesn't know that it's moving around? What if that circle was just here in the center, this little one, and that moon was going around at just at the right speed? Well, then the equation would be 2 cosine 10t and 2 sine 10t. That would make it so that as t goes from 0 to 360, 10t would go from 0 to 3,600, and the circle would go around 10 times. I know that it only made 9 petals. That's a little complicated to explain why. I'll give you some indication of why that happened, but this is half the equation. But that's the equation if the circle were located at 0, 0, and just that point was just going around and around. But the center is moving also. So the way the center moves, well, the center itself has its own equation. That's 10 cosine t, 10 sine t. That's the center itself moving. So the center just makes a circle with radius 10. And believe it or not, that's the answer. When you add those two things together, you know, the point that's on the circle, it doesn't know that the circle's moving. But when I add on the circles, x and y, the points on the circle, the center of the moving circle, when I add those two things together, the x's and the y's, the circle gets to move around, and it creates this pretty neat looking picture. Now let's see what you can do with the second scenario. And this one I'm going to try again, but I'm going to try to not distort this if I can. I'll just do my best to not distort it. So this one's a little different. For one thing, well, it's not. It's only a tiny bit different. There's only one difference, and that is that the circle is floating clockwise while still rotating counterclockwise. I'll show you what that looks like, and then we can analyze it. I'll give you a chance to work on that. So to make this happen, I have to turn R into 20, because it says it's going 20 degrees for every 1 degree that the other one does. Still 10 and 2, but to make the circle itself go clockwise, I have to turn D2 to -1. Let's make sure that works. There. So this is a little weird looking because see how the circle itself is floating clockwise while the point on it is going counterclockwise. So it ends up looking like that. Anyway, what I'd like you to do, and you could type into the comments, what adjustments do you need to make to this equation to accomplish the circles going clockwise instead of counterclockwise? You could type it into the comments. I see two very good comments. Melissa says, make sign negative. That would work, but it's even better. What would also work, what Ariel said, is change t to negative t for the center equation. They'll both work. It's a little bit better to do this one. This one's cosine negative t. Melissa, you can see that sine negative t is the same thing as negative sine t, so that would change this to a minus sign, whereas cosine negative t is the same thing as cosine t, so getting rid of the minus wouldn't change anything, but it's just a little bit better. Oh, this is 10 out here, and this is 2 cosine 10t and 2 sine 10t. Now, if it's floating clockwise, and it's also the point on it is rotating clockwise, if both of those are happening, well, then you'd have to put a minus there also. And here we have on the screen the equation for a small circle. I know I said it doesn't have to be a small circle. You actually can have a big circle going around a small circle. Equation for a small circle that's floating around. A cosine plus or minus r, depending on whether it's clockwise or counterclockwise t. And the other one is b cosine plus minus t, depending on whether the circle is floating clockwise or counterclockwise. So I'll give you a second to write that down. Now, there's a bit of a mystery about why when R was 10, there were 9 petals instead of 10, because it might seem that there should be 10. I'll show you something that may be convincing on that. So here, I'll bring this thing back down. First of all, what if R was 0? Well, if R is 0, oops, B is 10. If R is 0, oh, and let me bring, oops, R is 0, this thing's a little sensitive. I'll make them both go counterclockwise. So when that happens, you can see that it just makes a circle. Oh, Ariel asked, was that the equation first for a circle float? Yeah, that was the circle floating around the other one. Yeah, A and B were the radii of the two circles. R is the coefficient of the t on the spinning one. It's like the speed that the thing is spinning. So you see, if R is 0, meaning the it would just make a circle. It would just make a circle that's shifted to the right. Ariel, the R is, so far the R has been given to you. So then wouldn't the equation from example 2 be 20t? Sorry about that. Let me bring, what did I write there? Yeah, it should be 20. Did I write 10 again? Or did I? Okay, yeah, change that to 20. I'll fix that in a second. So look, when R is 0, you can see it just makes a perfect circle that's shifted to the right. But the funny thing is, when you make R equal to 1, you might expect to see something very different from that, or at least a little bit different. But take a look. Look at that. R equals 1 also becomes a perfect circle because it's rotating. You see the way that points? That black point is it's rotating so that the circle itself makes one full revolution in the time it makes one. And this is actually what happens when with the moon going around the Earth, like the dark side of the moon. That's because the moon actually not only uh, revolves around the Earth once every 29 and a half days, but it also rotates once every 29 and a half days. So one makes that, but look at what happens when you make R2. This is one of the more surprising things. When you make R2, it almost looks like a circle again, but it's not a circle. It's like closer to being an ellipse. Just so you know, long ago, when they thought that the sun went around the Earth and the planets, that everything went around the Earth, their calculations were not working out that well. So they had to decide one way to fix the calculations would be to make the Earth go around the sun. Another way to fix the calculations to explain the other planets would be for the other planets to still be going around the Earth, but the planets themselves would be going around these tiny circles as they went around the Earth. They were called epicycles. They still call them epicycles, and that's how these were used in astronomy long ago. Anyway, look at what happens as I make R 3, 4, 5, 6, 7, 8, 9, 10. So it just keeps on adding one more sort of flower petal each time. But it's always, at least for this type of question, the number of petals is one less than the R value. Okay, let me come back to here. I will change this to 20. Now, there's only 2 more questions for today. I'm trying to take this unit, this thing, a little slow, because if you try to do too much of this in one day, people get really confused. Okay, scenario number 3. Scenario number 3 is not yet the epicycle question, because this is still a floating circle situation. See, it still says, floating. But instead of floating so that the center of the little circle is on the big circle, it's floating so that the center of the little circle is outside the big circle in such a way that the small circle is like tangent to the big circle at all times. So it's almost like it's rolling around it, but not really, because if it's rolling around it, you can't control the speed. It will roll at a certain speed dictated by the scenario. Where in this one, I'm telling you that it is rolling, it's floating, and I'm telling you that it's going counterclockwise because you do have to be told. You can't tell from the picture whether it was clockwise or counterclockwise. And it's told the speed that it's revolving 5 degrees for every 1 degree. And you have to be told, in this case, it's counterclockwise. The spinning, the rotation is counterclockwise, and the revolution, they're both counterclockwise. This one actually has, anyone know what the secret to this one would be? How would we adjust what we've already done to make the equation for this one? There's just the smallest of adjustments. The previous one, the small circle was, its center was on the circumference of the big circle, and here the center of the little circle is outside the big circle. I heard you, we just add 2. Add 2 to what? Because there's a lot of places we could add 2. That's right. The only difference between this question and the last one, or the one before that maybe, so it's 2 cosine 5t. Don't put a negative because counterclockwise we leave it positive. 2 sine 5t. The only difference is it's basically going around a bigger circle. So it's not 10 cosine t sine t, but it's 12. So that's, we think of it as a float. It's floating around actually a bigger circle. It's the same answer you would get if you floated the circle, because the center of the circle, of the little circle, is going along a path that has radius 12, because it's not on the circle, but it's outside. So we have to add the 2 radii together. Here's the 10, and there's the 2. So it's really the same question. It's just, it's going around a bigger circle. The center of the moving circle is tracing out a circle of radius 12 instead of before when it was on the one with radius 10. I think I actually have this one here. So if I change B to 12, and change R to 5, and I think down here I could put the okay, so that smaller blue circle is the circle with radius 10, and the other blue circle is the one with radius 12. So you can see it's basically the same question, except it's going around a different circle actually. And you see this one really looks more like a bunch of cycloids together. Now, if I were to change, oh, I guess I can't multiply this one now. I'll worry about that for the next one. Okay, we have actually done 3 of the 4 questions, and there's only one left. But this one is a little, it has some tricky stuff going on in it. So let me explain the scenario. Here you have, we don't need as much information anymore. For an actual epicycloid, we do not need 5 pieces of information. We only need to know 3 pieces of information. We need to know the radius of the rolling circle. We need to know the radius of the circle that the little circle is rolling around. And what do you think the other thing we need to know is? Just one. Before we needed 5 things, but here it's only one thing we need to know. Type in what you think is the only other information we need. I suppose you could look at the question and you could see what information. You actually don't need the speed rate, because even if it's going slow, it makes the same picture. But we need to know, is the center of the small circle, is it revolving clockwise or counterclockwise? In this case, those are the only 3 pieces of information you need. Because when something is revolving counterclockwise, what about the point on the circle has no choice? It has to do something. What do you think that something is? If the thing is revolving, or I'll say rolling, if it's rolling counterclockwise, what has to be true about the point on the circle? It can't choose. It's predetermined now. And the answer, yes, it must also be counterclockwise. So it's implied, that the point on the circle is also counterclockwise. Here, we can see that when I bring up, and you have links to this, I bring up rolling epi, and we can see, watch the points on the circle. See, that looks right. It would look weird to you if the circle were rolling counterclockwise, but the point on it wasn't. Even though it could float that way, actual circle rolling must go like this. And here it is going the other direction. You can see that if it's going clockwise, the point on it would have to go clockwise also. Otherwise, it would just look wrong because it can't happen. But if something's floating, then that can't happen. What else is implied here, do you think? And here's the really thought-provoking part of today's lesson. Because the rate has to be implied from this. It's not given anymore. Anyone have a suspicion about what the rate is? Okay, I see circumference. Yeah, it is related to the circumference. And Jonas says 10 over 2. And then he says he lied. Is it a lie or is it just a mistake? Because a lie means you knew what the right answer was and you purposely said the wrong thing. And I see the word radius. Yes, well, it has to do, well, Jonah, you are right. It has to do with the ratio. So you might suspect that the equation that is R equals A over B. Sorry, B over A. Maybe. That would be 5 in this case. But there's a problem. Because when I actually do it, and this is done like accurately, the R did not become 5. Based on this picture, what was the right R? Notice the number of petals it has. And Jonathan, that's right, it's 6. So it's not 5. Well, in general, and then I'll tell you why that is, but in general, the R value is not going to be B over A, but it is going to be B over A plus 1. I'll tell you why that is in a second. But for now, it is going to be plus 1. Where is that plus 1 coming from? What's really the difference between a circle floating at a speed of 5 versus rolling at a speed of 5? Because the speed is 10 over 2, but where is that plus 1 coming from? I could explain that very well if I come back over here and go back to the floating EPI. And here I have, oops, hold on a second. I see. Let me bring back that circle and let me make this 12. And let me make this 5. So here is the situation where R was 5. and it makes 4 things. So this is the floating circle. Well, how is the floating circle any different than the rolling circle? It seems like it's exactly the same thing. Well, the secret to understanding where that mysterious +1 comes from is right over here. In the floating circle, look at what happens. Look at that point, that's sort of the horizontal point, and the point on the floating circle in relation to that point on the right now. So when, for instance, t is 30 degrees, when t is 30 degrees, that black point is at 150 degrees in relation to the small circle because it's going 5 times as much. So let's just keep that in mind. If you look right there, I hope you can see the black point is at about 150 when the circle is 30 degrees along its path. Black point's at 150, and it's 150 with relation to a horizontal line because that like point on the right of the small circle is at the horizontal. Compare this now, and this is the big reveal for today, rolling epi. When I put that point, this one, there, look at what happens when I roll that circle now. See that point? Because it's rolling, it's not floating. That point that was once horizontal on the horizontal with relation to the center is moving also. So let's go back to the 30-degree spot. That's about as, maybe I can get a little bit better than that. It is not easy. That's the best I can do. Okay, so when the small circle is 30 degrees along its journey, that black point is 150 degrees. It's gone 150 degrees, but not 150 degrees from the horizontal, but 150 degrees from where the horizontal now is, which was at 30. So that angle is not at 150, it's more like 180. And let me come back over here now. So when this is 30 degrees, this here is 150 degrees. But here comes big moment of the day. This angle here is also 30 degrees because this point here, which used to be over there, has also rotated 30 degrees. And that's why it is x, y, 2 cosine of, I'm going to write 10 over 2 plus 1 t. So it's b over a plus 1, 2 sine 10 over 2 plus 1. Or, I'm sorry, I think you'll understand it better if I say 10 over 2t plus t. And this one is also 10 over 2t plus t. I like that better. That plus t you need for the rolling circle versus the floating circle. The center of the circle is 12. It's not 10 because just like before, it's not on that circle. The center is going around a circle of radius 12. So 12 cosine t, 12 sine t. And that is the equation for the epicycloid. I summarized it here. You may not like this. You may prefer b over a t plus t. Or you might like b over a plus 1 t. Or you might even want to do common denominators and get what I have over here, b plus a over ac. I personally like this the best, probably. Get that plus t in there. Okay, so that was the goal of today's lesson, to get that formula. You can play around with the Desmo sketch. You can drag the sliders around and see what happens. There's homework questions about this. Tomorrow we will see what happens when the circle is rolling inside the other circle. And then we'll see, because the spirograph, that if it's rolling inside, it's called a hypocycloid, but the spirograph is not a hypocycloid or an epicycloid, because in epicycloid and hypocycloid, the point on the circle is on the radius, is on the circumference of the small circle, whereas the spirograph, the point is not on the circumference, it's like somewhere inside the rolling circle. There are, I think there's 3 equations for homework. It might be 4. Okay, so let me turn off the recording and see if there's any specific questions people have. Hold on a second.